I give the presentation without an audience, and then you just record it, right?
Yes, sure.
Good. So let's do it. So hello everybody. My name is Jueger Hesser. I'm giving a lecture today about brachytherapy treatment planning quality assurance. It's a radical introduction. I'm actually from the medical faculty of Mannheim, Heidelberg University, and we'll give you the approach how we tackle that from brachytherapy. The motivation is while tackling brachytherapy is one way of irradiating tumors, either having the source near or within the tumor. In particular, low-dose radiotherapy or low-dose LDR brachytherapy is a low-cost but very useful therapeutic option for tumor treatment, which doesn't need a lot of investment. So it just needs a minimally invasive access, and then we have a single contact treatment. So the patients often just stay a day in a clinic and then leave. So the success for that here is just depending on a lot of real experience and less on expensive machinery, like we know that from the teletherapy. So what I'm talking today is shortly to present a little bit the brachytherapy part in case it might be not that present anymore. What it means brachytherapy, then go directly what is meant with treatment planning, go on for the QA role, quality assurance role and techniques, give at the very end some conclusions and questions, and then we hand it over to my colleague Ernest, who just discuss the clinical implementation of these two things. So the objective for that here is that we have for this first lecture, what I'm giving here, as a theoretical background. Yeah? So how is the treatment planning generally done, how it's realized actually, and what is the background, how to, say, realize different quality assurance strategies. So what means brachytherapy? First of all, it's a radiation treatment. We cure tumors, or we work on tumors using radiation. And in brachytherapy, the radiation source is placed either within a tumor or very near to a tumor. The advantage essentially, when you're in a tumor, you have less problems irradiating parts far away from the tumor, which is the difference essentially to the teletherapy, which has to just irradiate from the outside and then just pass other organs, which might be radiation sensitive. We discussed between two classes here, intracavitary brachytherapy, where we place the source in natural openings or cavities, or we have the interstitial part where we place it into the tumor. We have a couple of differentiations between the dose rates. So especially we have the low dose rate, where we have typically radioactive isotopes, which are encapsulated and just implanted in tumor remain there. If on the other hand side, the high dose rate, where we implant a tube or a catheter or needle, as you call it, and then move a source within this tube and irradiate from the tube side in the tumor or next to the tumor. And this can be repeated for several times, for several days, but it's typically very short. And in principle, there's something in between, but this is not very often used. And the final part is the electronic brachytherapy. You have a very small KV source, which is then just either inserted in the tumor or placed next to this tumor. Especially focus on two aspects. First of all, we focus on the planning purpose. So we have two variants we discussed earlier. And HDR, the electronic brachytherapy, is one type of the HDR treatment, and the other hand side is the quality assurance. For HDR, in particular, the air afterloading techniques, which are those which are modern and often used. So how is now the clinical treatment? Well, what I'm doing here in this lecture, I reference the task group reports from the APM, because they're just going very much detail, and it's useful to read these task group reports. And what I'm doing here is because these reports give general recommendations, which are, say, how the planning process is done. This TG53 report, we're starting with, is not specific for brachytherapy, but essentially many steps are those which are taken brachytherapy as well. It needs indeed interpretation how this could be translated in a clinical workflow, because depending on the equipment of the clinic, there might be different variations. One have to deviate from these recommendations. These are in particular long and very detailed reports with a lot of references, which is good that you know why this or that decision was taken. What I'm doing, I picked some of these guidelines or parts out, tables out, and just present you these tables, just to give you a short entrance what aspects are discussed there, and then for the details you have to go inside, because the time isn't really enough for discussing it in detail. So the first step for this TG53 report is to find a clinical workflow, essentially, and identify the different elements which are required. So this is what I just picked out from one of these tables here. That's the treatment planning process. Initially, I have this patient, and if the imaging, what comes in the second stage, is not in the same, say, pose as later the treatment, you typically position the patient and immobilize the patient before doing the imaging as the second part. Once we have the imaging, then we have a lot of points here which are done on a computer. So we just get the data from the imaging system, define anatomy. That means we have to contour the organs at risk and the tumor. We have to define the degrees of freedom for our planning process. In our case, brachytherapy, we have the needles and catheters, which are inserted later. So the trajectories of these have to be defined. And we also have the seat positions in these catheters, or the dwell positions for HDR, which have to be defined as well. We come later to these here degrees of freedom when we're talking about how the treatment planning is actually realized. Then you have to define what you're actually doing is to define a certain dose, a prescribed dose to the tumor. And prescribed dose means that we have to simulate this treatment, and we can have two different modes. We can have an analytical model, or we could have take a Monte Carlo model. And then there comes a point which is in italic, because this is not a part of this TG53 report, but that's what we're actually doing. We do the treatment planning, which is not really mentioned in this table. And once this plan is done, we evaluate how good is the plan. So we look for the dose distributions in 2D, so in slices, or go through the slices. Look for the dose 1 histogram, the NTCP or the TCP, for example, as criteria. There might be other criteria how to do that, but this is just a selection of these. So it means we make a plan and first evaluate on the quality. If the quality is not good enough, we just repeat until we are satisfied, and then go to the last two steps just to implement it. It means once the patient is not yet on the treatment couch, we again align the patient again, and then transfer this part, this plan to the machine. So if you have a machine like HDR, the afterloader, then we have to transfer this here. And before we start the treatment, we just review all the aspects of the plan before we start, because in case there might be an error, we can just stop that and replan again. So this is the essential approach how TG53 is recommended in planning process. So I guess most of you are already working in a clinic or clinical environment, and you can just have a look how you have realized this work for this planning. I guess it's very similar to this here. You can compare in details with the TG53 report and can just check out by how far you follow this report or deviate, and if there's a deviation, there should be a reason for that. It's always a good point when hearing that to calculate or recheck their own approach. So question and answers of that here, what should you have learned are the individual steps of treatment planning. And now, taking this year as a basis, you can now compare treatment planning in brachytherapy versus teletherapy. So what is easier, what's more complicated, you can just check up with different lectures to see how far brachytherapy treatment planning is more or less complicated than the other. So now the second part, the treatment planning per se. And we're looking for the quality assurance. The rationale for that here is you take potential inconsistencies along the workflow. You have seen the workflow from the TG53 report that might lead to wrong planning data. So everything which could go wrong has to be checked. So at the end, it guarantees that everything works correct according to acceptance test of the planning system. So what are the targets? Well, here we have a couple of targets mentioned here. This imaging device, once you have the patient, you place the patient on the couch, then you make the image, and the imaging could be a problem, could be wrong. For example, CT might have artifacts, or the placement was not correct, and so on. The second could be the sources. So you might have problems with the sources. The third could be the device, like an afterloader, might have inconsistencies or problems which have to be considered. Then we have the software. And the software is digital. So actually, once the software is correct, you can expect that it works until you change something on the environment, either something in the software, something on the operating system, or whatever. And this could be inconsistent because it might not have been tested when the software has been written. So it has to be checked again whenever something changes in this part. When this is done, essentially as part of the planning, then you get a plan. This is documented, and this is important because the documentation tells how much dose distribution. For example, for later re-radiation, we have to know the exact values. This has to be checked whether the documentation is correct. And these are all individual elements. So if you check all individual elements, you might say it's correct, but that's not true, because the interfaces between elements, from the imaging to the planning program, there might be problems from the interface. Yeah? And this can only be found out if you check all things together, working together, and this is called the system test. So for this QA, we have the TG56 report. There's a lot of detailed tables, what should be considered, and so on and so forth. I just picked out one table and discussed it in more detail, that you see what are the different elements. So here, for example, this is one of the table number 3. I took out, it's here the function, the benchmark data, and the frequency, how often you do that. And here you have the first verified geometric accuracy of I/O peripherals, digitized CT, ultrasound, and so on and so forth. Yeah. So what is done essentially here is one takes phantoms, typically, or things where we know the geometry, and just measure that and check it out whether it's consistent with the parameters from the, say, phantom, what you know. And this should be done repeatedly, monthly, typically, because it's expected that if there might be a problem in the imaging system, this occurs not often, more often than at most 1 month. The second here, input parameters for all pre-calculated single source arrays, recommendations from the vendors, calculate drawings, and this are to be done typically initially, yes, always initially, before you set up anything, it has to be tested, but here also we're going to do that annually. Again, about the source, verified dose, dwell time, treatment time calculations, and so on and so forth. So we have the dose rate tables here. You can just go back to manual calculations, things like this, what is recommended from the vendor side. And again, always initially, annually, it's recommended, it's related to doses. Whenever something changes on the software, libraries, environment, it has to be checked again. Then accuracy of single source isodoses, so it's directly about the source in the software part, so how it's described. So again, point source output, again, initially or something changed on the software. So once the software is up and running and tested at the very beginning, then nothing will change. So once you have correctly imported single source isodose and everything's fine, the same is for multiple source isodoses for potential plan rotation or consistency of the printed plan. By the printed plan, whether it's okay, this should be done for every clinical use, because actually for each patient you should just check whether everything is fine, because it affects the patient directly. And then you have the coordinate reconstruction, again, pure software stuff here initially, and this same stuff here, accuracy of electronic download and treatment parameters of the loader, it's a digital process. So it's initially new software, and for each treatment, well, you just verify the correct thing here, because it might go wrong for any reason, defect cable, whatever, so it should be just checked again. Here again, dose 1 histogram, that's the pure visualization part, only software dependent, optimization software the same. Yeah. And the overall system test, it's digital part, so again, also initially, but since it might affect other things, so that's also recommended to do that annually. So take home message for that here, how far can these steps be realized? Well, actually, you see most of these are done initially, and this will come later, back when you have the acceptance test. When you get something new, then you have to check it, and this is anyway something you have to do, so that's not so much you can do differently. And here, what are the reasons why parts are not realized? This might be the case because you might not have this in that device or other reasons. So, questions and answers. What are the relevant elements of the QA/Q, and what are the reasons to perform the QA at the end? Now we come again, go away from the QA part, come back to the treatment planning again, and we're looking for the dose calculation process. For the dose calculation, we have two options. No, we could just take an analytical model, or we could take a model-based approach like Monte Carlo or Boltzmann transport, whereby Boltzmann transport is very seldom, Monte Carlo occurs more or less more often in recent time. What I'm doing, I'm focusing on the analytical dose model, because it's more or less everybody's using it, and here the analytical dose model is just typically derived from the TG43 report, and I go a little bit more in detail on that here. Some variations of this report recently, which are discussing variants or different things here which are related to that, but essentially just the initial part here remains the same, so I'm just giving a short detail how the model, this analytical dose model here, what we have, is actually realized. The very important part is, and this is it's pre-calculated, or it's a parametric model. The very important part is that this works only in homogeneous tissue. Yeah, so homogeneous means water equivalent, essentially. It won't work when you have air cavities, when you have bone next to it, because this might be definitely a problem. And in this case, there's a must to take other methods to be reliable, not like Monte Carlo dose calculation, because otherwise you might expect errors. If these errors are not important for your planning process, you might tolerate that. If they're important, this might be critical actually. So let's now go for this TG43 dose model in details. So the most often used model, you should understand how it's built up and what are the limitations of this model. But this is a good idea to see how such models are constructed. So at the first, we define the source. The source is typically a cylindrical source with a certain length L and a diameter of 2d. Yeah? And we place it in a defined coordinate system to characterize it. So this coordinate system is that this elongated source, yeah, just has the orientation of the z-axis, and the center of that here is just the origin of our coordinate system. It's cylindrical, so we can just take a 2D sketch because it's just rotational symmetric. And what we do here, we have here another axis, the second axis, and distance from centimeter, we have a reference point. Yeah? So R0 is 1 centimeter, and theta 0 is 90 degrees. And then we have a dose point, what we want to calculate from this given source. And this is P, the different distance R from the origin, and different angle relative of this vector R, origin to the point, and we have this angle theta. So the model describes the dose rate at a certain distance R, here this R, and this angle theta, yeah, as a product of different factors, as you see here. So you have these two factors which are related to the source. These factors are related to the geometry, and these two factors are related to deviations of a simple model, air model or vacuum model, yeah, here for the radius alone, and a correction with the angles. So let's have a focus on the first two, which are described in the source. So whenever you have a source, you can define the SK, this first parameter, is here the K dot, as function of d, this times d squared. D is the distance, so in this case, we measure it relative relative to this reference point. So in this reference point, the distances are 0, this is 1 centimeter. Yeah? And this is the air camera stress. Air camera rate, and this is the air camera stress. Air camera rate in vacuum, so we have no material, and so for example in air, and this characterizes the source. And this is nothing else, just that we compensate just the radiative drop from distance, so that we can just assess how is the dose in a certain distance, and we measure it. Here we measure the air camera rate at this position and relate it to the source, which is this point here. The second is we define dose rate at a certain reference position. So now there's a difference. The difference here, it's in vacuum, and here it's in matter. Yeah? So it means we have a relation, we have a factor, no? So here the dose rate at the reference position divided by SK is lambda. And this defines, if we have now not air but water, and we measure that, then we get a correction factor lambda. So it means these two define what is the dose at this reference point in water, the dose rate. Now we have a point, you see we have an extended source, we have not a point source. In the case of a point source, we could say that the geometric factor is R minus 2. Yeah? So it means we have the geometric factor at the reference point, and this geometric factor at a distance r. Yeah? And if it's a point source, then it's clear that the dose rate drops like r2 minus 2 relative to the source. And since this is the reference point, then we have just correct for the reference point as well. So we take this ratio. If you have an extended source, line source, then we have here a little bit more complicated formula, which is describing the same. Now let's come to these two factors. So L is the length. Here just I have written x, but it's meant the length of the source. No? The length here is the source. And what we're doing, we just say or describe by this term, how is the dose rate drop off relative to the reference point as a function of the radius, of the distance. So we go along, as you go along this red line, vary that, and this describes how this works. This is what we have to essentially do. We have to take the ratio of the dose rates, given this theta 0. So this direction is theta 0. Yeah? And for r, so a different distance relative to r0. And then we have just geometric parts which are just compensating these dots. So this means we describe here how it changes, and typically we approximate this by a polynomial. The second part here is that we might have deviations if you just go along this green line with the point P. Yeah? So we keep a fixed radius and just vary the angle. And do that for different radii. And this we call an anisotropy function, fr theta. And same idea like here. No? So we take it to a reference point. Now its reference point is here, no, on the red line. The red line intersects with the green line. That's the reference point. This is just the point somewhere on the green line. And we have here the geometric factors which are compensating it. So this is a non-isotropic dose formula. So that means we have now discussed all the things. Yeah, and you see source characterization, geometrical part, you have a drop on the radius, and you have a drop or variation on the angle. If you have a very well-defined source, then there's no angle variation, so this is just a constant. And here this just describing the absorption, because you have the spectrum, and according to the spectrum might have different absorption characteristics, so it just describes actually over the measurements how the dose drops over the distance, ignoring the geometry and the source part. So the questions answered this year are: what are the components of this model? No? What are these individual components? How could this be measured? No? I mean, looking at these here, camera rate, yeah, here this geometric factor, this part and this part, and look here, what are the areas where it's defined this way to measurements. So this is how can do these measurements, and from the lectures about dosimetry, you can just relate that how you might do the measurement actually with a certain chamber or so. And where do you see limitations? But obviously, what we never considered is any inhomogeneity of the tissue or material what you radiate. So this is it. That's the main problem of this analytical model. Yeah? And whenever this is not satisfied, or whenever this is not correct, then we have to go to another one. Now comes the inverse planning. So many still doing this planning by hand, but expected that in future this is more or less done by software. And what I'm doing is describe you one approach of how this inverse planning can be realized. Actually, what we're starting with, we have a 3D image, so volume, yeah, where we have outline the PTV, planning target volume, which is, since the source is in the tumor or next to the tumor, we have no relative motion between source and tumor, so we consider that it's the same as the clinical target volume. And we have outlined the organs at risk as well. And outline means that we do it just on ultrasound, CT, or other modalities, just do it slice-wise and just control slice-wise these different structures. We define potential catheter positions in the volume or needles in the volume, so the trajectories are defined, and then we have to characterize what are the potential positions of the seeds or 12 positions. These are the degrees of freedom. And then this is an interesting part. If you have seen how the planning is done for brachytherapy, one takes a volume, and for each voxel, one just computes the dose. Here it's typically different. One uses so-called dose points. Dose points is just a subset of the voxels, which are taken into consideration for the PTV and organ at risk in the volume and on the surface. And typically it's uniform distributed over these volume and surface. Here's just pictorial part. No? So you have the trajectory, here potential positions of the seeds or 12 positions, and you see the blue points, organs at risk, and the tumor are potential dose points which are even distributed. And they're not on the seeds typically, otherwise it won't work, but just next to that and on the surface, which I have not drawn here. So this is what we define. The reason for this here is just essentially to be quicker. We can pre-compute this here, and you see that in the moment that we just make that cheaper than just taking a full volume boxes because it's more to calculate. So now what we can do in the inverse treatment planning process is to pre-compute the dose according to the GG43 formalism. What does it mean? We know, because of the definition, where are the sources or 12 positions, where is the potential to irradiation point, and for each of these points, we compute how much dose for maybe unit time is just deposited in each of these dose points. So it means, if you go back, for each dose point I, and for each source j, we can pre-compute the dose. And since we have two indices, this is a matrix. Dimensions are the number of dose points and the number of sources. Typically, we have a reasonable distance between the source positions, which typically 2 millimeters, so we have no overshooting areas, because otherwise it doesn't make so much sense. And this just limits the number of sources, and therefore we have a not too big matrix. And the dose for a certain dose point, I, is therefore just the sum of all sources, the dose matrix dij times a variable xj, which is, in case it's the seed, LDR, if there is seed, then xj is a 1, or there's no seed, it's a 0. In case of an HDR, we have the dwell time, it's a real number, between 0 and the maximal t value. So in this interval, you have a real number, which is taken instead. So it just mentions for the HDR that just the weight of this dose, pre-calculated dose, and this was done for unit time, then it just says how much dose if you have a certain time it resides on a certain position. And for a seed, it's just 0, 1. So that means if there's no seed, there's no dose. And if there's a seed, that's the unit dose dij, which is just added to the dose for the dose point. So the important part for all this here is that we have prescribed doses. It means we have an upper dose for organs at risk, and we have a lower dose for the tumor. Reason for that here, the NTCP means sensitivity of an organ at risk is defined or characterized by the upper limit of the dose, and the tumor control is defined by lower limit of the dose. So it means what we define our weights are, say, constraints and penalty values. And we have differentiate between the case where the dose, the I, what we have calculated, is below a prescribed minimum. So that in case of a tumor, if it's lower than the minimum for a tumor, then we have a problem. If it's violating constraint, or in case of an organ risk is bigger than a Dmax, then we have a problem. And we have no problem if it's in the interval between Dmin and Dmax, so between the min and max doses which are prescribed, then you have no penalty. Otherwise, you have a positive penalty. In this sense, if D is smaller than Dmin, then this is negative. And if D is bigger than Dmax, this is also negative. This is a rate here, and so get a negative value. So the objective function is what just we minimize the penalties. So we take the absolute of these here, and we minimize the penalties of this here. And because often we can't satisfy all these penalties, we have to compromise of these. In case of HDR, we often include, say, the dwell time variation. That means if you go from a source position Tj-1 to source position Tj, just include here this difference as well and minimize this factor. So what we're actually doing in the planning process is to set these weights. We set these weights that we get at the end a plan which is reasonable. An individual plan which is, we say that's fitting very well the expectations what we have for the patient. And say that means when we do a plan evaluation and not satisfied that what you're doing essentially you just vary these weights until you're satisfied. So here are a couple of questions which are related to this. First of all, dose points, how to select these dose points in the target and organ risk. What about the typical question, which is what I have not discussed, what might happen if you have tissue deformation while implanting the sources? HDR, for example, you have a needle which is deforming that. What is the consequence of this here? Make it clear what errors might be included, which are not mapped here by this model. Here, how to select the trajectories, set of tubes or catheters for HDR and the seat positions, how to do that. Where should you place it? Does it make sense? Where does it not make sense? And what is the reasonable minimum distance between seats or dwell positions, for example, in the HDR part? So this was essentially the planning process. So what we have now seen the workflow for the planning. You've seen the dose model, how to calculate the dose for the planning. We have to see how that's calculated in this treatment planning. We have seen how, what things are generally to be considered. And now we come to the QA in detail, the quality assurance. And here comes the role. It's to verify the correct functioning of all devices and elements in the treatment procedure. So a couple of steps what we're doing here. And this QA is bigger than we have just only for the planning. So what we have so far discussed is just the QA for the planning. And this is now the channel QA for this treatment. And it starts before you build up your treatment site. So it's site planning, radiation safety shielding has to be considered, purchase, acceptance testing, commissioning. These two I'm discussing in more detail. You have to establish a quality control program, that's training personnel, and then starts the treatment. What you have discussed only is the treatment part. So a couple of things, especially these two, are important. You have to focus on these here as well. So QA role techniques. So this is a very principal part. What are the two issues what the QA is doing? First of all, if you have a new device. The new device, which has never been used, might have a certain risk which is associated before you start using them. For example, during the transport, it might be damaged, or that the staff has no experience how to correctly use the device because they have never seen this device before and never worked with it. Might be like difficult to understand the details of the manual and so on and so forth. So that means what the first risk is to place a unit into clinical operation. This is the first operation, the first treatment is associated with the first use. Once the personnel and in the clinic this has been used for a while, there's a different class of risks which is coming during the usage. So the devices might degrade over time, wear out, mechanical devices, drop effectivity of sources, and events that might affect the correct function of the devices. So what we have to do, we have to maintain its reliable performance. So these are two issues, no? Very beginning and during the treatment. And this is just here a link where this is discussed in more detail. So I call it first use risk. What you're doing in order to overcome that is that we do a set of predefined tests, which are typically defined by the manufacturer because they have the know-how, they built the system, and they know what are the critical parts which have to be tested. Or if not, definitely often task reports from the APM which help to do that. This covers the set of potential errors that might occur, or experience says that there might be a set of errors. One can calibrate the system initially. Calibration is very important because you rely on these parameters, and this allows to train the personnel correct usage of the device. This test has to be done at the very beginning when first using the system, but often it's recommended to do that yearly or whenever anything happens with the device, it was done. For example, you get new inverse treatment planning software that's delivered with the PC and tools. So you do commissioning, verify in example cases that it delivers the same result as the old program. Be careful on this here, what is written here. It can only deliver it if it's taking the same dose model, for example. If not, if it go from analytical dose model to Monte Carlo, you might have differences. Yeah, so take care that it's not exactly the same. Often it might be, but similar. Huh? If everything was fine before, then it should be very similar. With no degradation over time, the software doesn't change. Yeah, so there's no need to repeat this commissioning. However, whenever you change something slightly, operating system, libraries, whatever, the software has been tested on a certain environment. And verify that it works correctly. If you change the environment, that's not a guarantee. There might be a reason why it might not work, so we have to repeat that whenever some of these changes occur, and to guarantee that there was no conflict. Risk during usage, that's a different story. So while using the device, it might change its parameters. Risk that the functionality of the device might degrade over time to wear, usage, uncontrolled events, collisions with other objects, mechanical device, whatever. In order to control whether there's a deviation of the function of the device, we have to perform predefined tests, which are typically provided by the manufacturers or vendors and have to be performed. For example, you can recalibrate the system. In case of large calibration errors, you have to go back to a QA plan and just to have to repeat that more often. Sorry? This also allows to retrain the personnel. If somebody who is coming, then have to be trained on this device. For example, let's take an imaging detector, and when you're using that, we irradiate the detector. It means it receives radiation damage, and over time, sensitivity changes, that means the gain, or dark current changes, that means the offset for each pixel. So that means over time, we have to do a calibration. That means we have to do a gain offset correction that is compensating for these deviations over time. Or so when we have to do that, so it's a question how fast the detector degrades, depends on how often it's used, what is the dose, stability of the detector materials, and so on. And this is typically given by the manufacturer because they know all the details and they know the time to failure or time to deviation, and from that they expect when the calibration should take place. So the question is, if looking at the brachytherapy unit, what are the risks at the very beginning? And for the planning part, we have already seen it. First-time risks, which you have to identify, and which of these risks are coming up during usage, which you have to identify your brachytherapy unit. So I want to have here a couple of QA types, especially these first two are important. This first acceptance testing. So when you have a new system, you're measuring the compliance with given specification for the device. That's what we call acceptance testing. Compliance with specification. So we verify that it fulfills all specifications by measurement. The second is the commissioning. You have a baseline performance, you measure that it fulfills a baseline performance. These are different, and I'll come to that in a minute. Then we have a periodic QA, monitoring reference performance. So we have a baseline or reference, and we just over time, we measure that it's fulfilling this performance criteria. We have so-called quality control tests. Each significant change, update, whatever, monitor potential changes of the performance. And then you have patient QA, and this is the very important daily part. You validate the correct functioning for each given patient case. So here coming for the acceptance testing. The acceptance testing is measuring the compliance with given specification. So we have typically three parts. We have the safety checks, we have to be verified, mechanical checks and dosimetry checks, which are important. They are determined by manufacturer spec sheets, and procedures checking is well defined, for example, given by the manufacturers how this acceptance testing should work. So looking for the specifications. A couple of specifications which are defined here. Commissioning detects the accuracy here. Acceptance specification, commissioning, accuracy of the system-specific parameters. It's different. So we measure that it fulfills the safety requirements, is acceptance testing. To measure a certain dose rate is commissioning. So we enter data into, in this case, a treatment planning program. Just take a phantom case, or for phantom, we just make a plan and verify this plan by measurements. So why this? Because this is a software, and what we do, we realize a treatment, and when we realize, we have to check out whether the plan is correct. That's what we do, system-specific parameters, whether they're correct. So we have to have QA procedures which are doing that, typical types of phantoms, typical type of plans, and so on. And the typical part here is the nearer these phantoms and the plans are to daily treatments, the better is, or the higher is the chances for potential problems. Another point here is staff training and do commissioning. It's a good starting point whenever somebody comes new or when training should be repeated, is to do that. Because, by the way, this is on the phantom side, and you can try out how this works, how the treatment process is working, how the planning software is used. When we do this here, you just get accustomed to how to do that. Here, for example, QA for an HDR system. We have a spot check. HDR can consider that we have these afterload. We have a catheter which is in the patient or in the phantom, and on the tip of a wire, which is in the afterloader, you have the source, and then the afterloader shifts the source into the catheter and retracts it with a certain speed. And spot check is correct stopping position of the source, which should be done daily to verify that everything is correct. Time test should be less than 2%, so if it resides a certain time, the actual timing should be better than 2%. The symmetry, that's a calibration, should be smaller than 3%, and compared to the treatment planning system, better than 2%. Documentation should be correct. And the applicator does initial test and year repetition, whether this is okay. Treatment planning system according to TG53 should be tested. And if there's image guide, if it's an ultrasound, there's a TG128 recommendation, which should be considered as well. So here are summarized the task group reports, what I'm mentioning here in this lecture. We have here the TG53 brachytherapy physics, TG42 afterloader system, which I have not mentioned, but this is for HDR, the important part. TG43, the dose model, what we take, to the TG53 QA for treatment planning system, and for ultrasound, we have TG128, ultrasound used in brachytherapy. So we slowly come to the end of this first part of the lecture. So the first is, what are your acceptance tests in your brachytherapy unit, by how far they are compliant with the TG recommendations, and how improve this procedure to be more compliant. The second is how to realize the commissioning, again, acceptance test, commissioning, what were your conformance measurements, what is your QA plan, and how was the training performed. Very important part. So how could this process be improved in your clinic, be more compliant with task group recommendations. So the final slide here is conclusions and questions. So first of all, this lecture was to get an introduction course overview on the concepts of brachytherapy planning and QA. I didn't mention all the variants what we might have in brachytherapy planning, how this could be done. I left out completely optimization part because it's something we don't care so much as pure mathematics, pure numerics, but I mentioned also QA, few QA elements, and especially the task group reports, which are important. Focus more on the modern parts, not on outdated parts, which were used earlier, and have done the lectures to have anchors and basically understand underlying methods. That's what I'm doing. What I'm not doing is actually, yes, we have still the task group reports, and to really carry on what you have seen here to your applications, you have to take these, read in detail carefully, and just try to follow these recommendations. But keep in mind these radical concepts, what I've introduced here, why we have these first use risks and the risks during usage. Yeah. What are the reasons for that? So you might read that here and there in the task reports as well, but this is essentially the summary, and for that reason, I have just given this short overview. So now, by this year, I'm finished with this lecture. So, questions. Are there questions from the audience already, or I don't know? Hello?
Yes. Thank you very much. Any question, please? Oh, okay. So you can type your question, or you can just speak. I'm seeing German. Okay. Thank you. Quite nice. All right. No question. So I'll actually replay this class, so you may receive a.
Yeah, that's one question. I got it from the chat. So the question was, is it only TG56 that can be used for brachytherapy? Let me come back to the. So here you see on that slide 56 is brachytherapy physics. Yeah. So it means it's just discussing this part. It's not discussing. Oh, again, the next question. Sorry. No, let me first. So, TG56, can that be used for brachytherapy? Only can be that used for brachytherapy? Yes, it's brachytherapy physics, so it should be used. Yes. The second question is, can TG53? 53 is this here, Q8 for treatment planning system. This is a very general part. Yeah. Let me go back to the 53. I guess it was the first what I've mentioned. So this report is a general treatment planning process. If you read it carefully, it's more for the teletherapy, but the steps what we have, and you see these steps here on the slide, are essentially, say, mostly the same as we have it for the brachytherapy. I mean, you have to, when you do planning, you have to do this anatomy. Yeah, so you have to do the first image, then the anatomy, patient positioning depends. You know, when you have an HDR part, and then you have first a CT, let's say, insert the catheters. Once you have insert the catheter, you make a second CT, then you see the catheters, and then you have not to position the patient or immobilize the patient because the catheters are the reference. Once you see the catheters in the CT, then you're done. For the LDR, for example, prostate, you have direct field ultrasound, and when you do the imaging, it's directly related to the patient. So there's the immobilization essentially just when you fix the grid and the ultrasound to the patient, then this is just the positioning, let's say, yeah, right? The other parts, degrees of freedom, dose calculation, inverse treatment planning, and plan evaluation is always the same. Yeah, I mean, at the end, here the ways you do plan evaluation, you can do the same way as for the teletherapy. Need not. No, it depends what is your internal approach, and you can just go to this report to see what they recommend, and you can just stick that as much it makes sense for you. And the final parts, the implementation depends what you're doing. For HDR, transfer the plan to the machine. Yeah, it's similar like transfer the plan to the Linux. For teletherapy, patient alignment, in these two cases, as I mentioned, it's not necessary, so we have not to take that into consideration. And plan review is always recommended because not to harm the patient. It's always recommended just to check before we really do the treatment. Yeah, that you check, okay, is everything okay? Was any error in there? And then you can just go on. So I hope that I answered these two questions over the chat. Are there other questions coming up?
Oh, okay. All right. Thank you. So, Professor Jueger, please, I wanted to ask, can the students send you their questions after watching the video? Because many of them are going to watch the video and then they typically will send questions.
Yeah, yeah. So actually, they can send me questions over an email, and then you maybe can distribute the email to the other audience members.
All right, no problem. Yeah, thank you very much.
Thanks a lot.
Yeah. All right, great. Okay. Thanks for.
So.
Okay, yeah.
Can you share my screen?
Yes, I can share.
For the clinical part?
Sure.
Hi, Ernest.
Hi.
Yeah, so you have the link for the screen.
Okay. Can you see my screen now?
Have you clicked it?
Okay, I have to click it.
Yes.
I have to click share, right?
Yes.
Okay.
We're waiting for it.
So can you?
I think it's going to show shortly.
Can you see now?
Not yet. Wow. Can you just try click it again?
I'll do it again.
Yes.
So
yeah, we can see it now.
share.
Oh, we missed it.
You can see now.
No, we saw it just now, and then we missed it again.
Okay. I'll do it again. You have it?
No. Mm. Yeah, we have it now. Perfect. Perfect.
Okay.
Yeah, so you can just
okay. Okay. Let me just continue with the clinical part of what Professor Hesser presented.
Yeah.
But before I move into the clinical part, I would like to give some motivation on why one should have low dose rate prostate brachytherapy as an option in a clinical, in a comprehensive cancer care setting. This is a randomized study that was carried out by Peter Grimm and others to compare the effectiveness of different treatment modality for different for different risk groups. So if you, for the first curve, for the low risk group, you can see for monotherapy for just seeds, which is in blue. You see that here for the monotherapy, you see that the patients, they are doing quite well after several years of the therapy. And here you have surgery, which is not doing that quite well. You have external beam therapy, and you have photon therapy here. Then if you go again to intermediate group, for the intermediate group, you also see that monotherapy, seeds alone, that they are doing quite well, and seeds together with external beam, you see that they are also doing quite well compared to other treatment modality. Likewise, if you look at the higher risk group of their study, you also see that brachytherapy is doing quite well compared to external beam therapy and surgery. So I move now to the quality assurance procedure. As Professor Hesser mentioned, it's quite a deceptive procedure with many blocks that one has ready to take care of when it comes to quality assurance. So it's important to identify where things can go wrong and to verify them. Here I have an end-to-end quality assurance pathway in low dose rate prostate brachytherapy. Of course, not all the points, I don't have all the points that one has to take into consideration here, but you have, I'm going to go into details. This is just to give you an overview. Here you have the treatment planning system commissioning. You have the other equipment commissioning like the stepper, the ultrasound. Then you also have the physician consult. What is implement? What I try to show here is that the physician, brachytherapy is a teamwork. It's not just left on the physician. So you have different professionals, you have different professional group interacting with each other. So maybe as a medical physicist, you want to know what groups of patients are you treating. Then you go to the planning. You don't want to have your patients sitting lying on the treatment table, and then you suddenly realize that actually that's not the patient we are supposed to be treating because the patient doesn't fall into the right risk group. So you want to do pre-planning, you want to do volume study. Then to source delivery, you want to make sure that the radioactive source, they are being delivered in time. You want to make sure that they are not contaminated. And you want to make sure that the right source and the right activity is being delivered. Then moving up to the system setup in the operating room. So you want to be sure that all the different equipment that you have, that are well connected, that nothing goes wrong during the procedure, because the patient is anesthetized, and you don't want to have a situation where the ultrasound is not, or the TPS is not picking up the images from the ultrasound, or you cannot change from the longitudinal view to the axial view. To the intraoperative planning and source implantation, you want to make sure that the urologist with whom you are working with, or the radiation oncologist, that they are putting the seats, they are placing the seats where you want them to be, so as to have a good coverage of what you are treating, the prostate that you're treating. I will just keep this pre-operative planning because it's also included here. And then for the post-implant, the post-implant is what do you do after you have implanted your seeds? What do you do with the remaining seeds? How do you make sure that there are no seeds missing? So you have to make sure that the environment is left, is not contaminated in any way. And then you have the post-implant dosimetry. The post-implant dosimetry is mainly, when do you want to do the post-implant dosimetry? Do you want to do it immediately the next day after the implant, or do you want to do it several weeks after the implant? What are you taking into account? Are you taking into account the trauma that was caused onto the prostate? Because the needles that are being placed through the perineum into the prostate, they cause trauma, making the prostate to swell. So when do you want to really do your post dosimetry, so that you know that you can be sure of the quality of the implants that that was done? So as I said, I'll go into all those things. Commissioning, which was mentioned, is a very important, it's one of the most important quality assurance activity that you can do to prove that the system specifications are accurate. So when you get a new system, the vendor sends you a list with all possible sources, radioactive sources. Here you have cesium-131, you have iodine-125. You have iodine-125. Iodine-125 is not iodine-125. It depends on the vendor, because the vendor, they have different designs. So you want to know what your vendor is providing for you, what kind of design is the vendor providing for you. So with those specifications, that's what you import into your treatment and planning system, and then you go now to verify if the treatment and planning system is doing what it's supposed to do. The commissioning of the TPS, what we use in our clinic, we use the variant TPS, which is called VariSeed. So it comes with a couple of tests for the user. Here I have 6 tests. You have the dose point calculation, which is described in the TG43, which U stands for the update that was made to it. I think that was 2004. The second test is isodose level, volume and dose volume and dose volume. I mean, when you contour your prostate, is it the right volume that the system is presenting to you, or is giving you something else? The anisotropy function that was also mentioned in the previous lecture, data transfer and handling, what is happening between your ultrasound and your TPS? How are you acquiring the image from your ultrasound? Are you acquiring it directly, or are you acquiring it through a frame grabber? Then you have the stepper. Is the depth accurate? The angle tracking, is it accurate? So all these things you have to test. So all these things are things that Professor Hesser already mentioned. So this is the clinical aspect of it. So now to the dose point, and on the left of your screen, you have the dose point, and on the right is the highest dose level. The dose point is mainly, you see these two green spots here, those are radioactive sources, iodine radioactive sources. So you place one in the middle, and you have the points. You have those points. You do a snap of those points, and as I mentioned previously, you have the specification of the source you are using. So in that specification, you have what you are supposed to get. So you look up on the table that was provided to you by the vendor if the doses at this point is what is required, if it's accurate. And then you place the second point, and then you try to find the sum of it. Likewise, with the isodose level, you place one source and you look at the isodose level. If the isodose level, they are supposed to be where they are with the distance, with the increment in distance. And this should be within 1%. Likewise, for the dose volume test, you are mainly finding out if the treatment planning system is calculating the dose volume the way it's supposed to be. And this test is supposed to be within plus minus 5%. Likewise, for the anisotropy function test, you have a table which is also provided in the task group DG43. So with the anisotropy, just as Professor Hesser explained in one of his slides, so you can, most of these things you can do a hand calculation with the formula that he showed. You can also, at times, I recommend doing a hand calculation because it's quite easy to do a hand calculation to also verify as well. I'm sorry?
Yeah, you can continue. I think that was just a hit.
Okay. So, as I said, it's recommended to do a hand calculation because when you do a hand calculation, you get a better feeling of what the system is supposed to, the output of the system. So with the anisotropy function, you mainly look at the doses at different points that are provided by the vendor itself. Then you can also do a hand calculation. You can say, okay, I want to find out the dose at a certain point, and then you use the various factors that were provided on the table. For the ultrasound, you mainly do the longitudinal position and the rotational tracking to find out if it's quite accurate, and this should be within 0.5 millimeter and 0.5 degree. There's this good review from Dwele and from 2017, which I recommend for anybody doing this to read. And then you also have the template. All of this I'm going to show with the various seats. I'm going to demonstrate with the various seat. The template, you want to make sure that the visual template and the physical template, that they are accurately aligned, because you don't want to tell the physician, the medical physicist who is giving the instruction to the radiation oncologist and the urologist where to place the needle. So you don't want to tell the urologist where to place the needle, and he's placing it there. Meanwhile, the templates are not aligned. So at the end of the day, you are treating something, you are giving the patient a totally different treatment as planned. So for the guidance template, the ultrasound template, and the planning template, they should be correctly aligned, and the tolerance should be within 1 plus 1 millimeter. Then it's also important to know your radioactive source. Here I have iodine 125, palladium 103. These are the ones that are mostly used in our clinic. We use iodine 125. It is not the half-life of a radioactive source that makes it suitable for an implant. What makes a radioactive source suitable for an implant is the energy. With iodine 125, the energy has average energy of 27 kilo electron volts, which is suitable for prostate therapy for us, with a decay of a half-life of 59.4. And for monotherapy, what is recommended is 145. What we do in our clinic, we go for 160 gray. Yes, why 160 gray? Well, we do 100 and we prescribe 160 gray because till now we haven't we try to keep the organs at risk at the recommended dose tolerance. So our patients are doing well. So if it's important when you're doing such a treatment and you decide to do something else, so you have to back up why you are doing that. So we started.
Hello.
And our patients are doing well in regards to the organs at risk. And if you are doing a boost, then we do 110, which is recommended here. The specification for iodine, here you have the specification for iodine. We use the BAT system, which is iodine is a liquid on an aluminum wire. It has a length of 4.55 millimeters, and a width of 0.8 millimeter. All of this you can get it on this report from Rivat. So the BAT system, as I mentioned, that we use, here you have the loader. The loader is used to do the configuration. Some vendors, what they do is that you tell them what kind of configuration you do need, and they are going to configure it for you, and your needles, they already come loaded. But for the BAT system, the advantage for us is that, or why we like the BAT system, is that we can configure the seed strand ourselves. And there are three possibilities on how one can configure the seed strand together. You have the seed space seed, you have the seed to seed, and you have the seed space extended space seed. So you have these three possibilities on how you can configure your seed strand. This is another clinical relevance graphic. On your hello?
Yes, just continue, please.
On your left, you have the dose rate as a function of time after since the implant for monotherapy. Just to give another rationale why we are doing iodine, you see that iodine with the red curve, you see that iodine is below, it's 1.8 gray on the first day of the implant. If you look at palladium, palladium is 5 gray on the first day of the implant, and you have cesium-131 with 8 gray. So you see that, or you realize that iodine is doing quite well and is comparable actually to external beam, to the fractionation that we do in external beam therapy. And you also agree with me that these patients with cesium or palladium, they have more acute effects than patients with palladium. Of course, the reason for that is because of the half-life. Palladium has a half-life of 17 days, and cesium has 9.7 days. And here on the right, you have the dose rate for typically used seed strain. For cesium, the typically used strains are 2. Iodine is 0.5, and for palladium is 3. Here is also, you see that palladium is more than 6 times more than iodine, and cesium is also more than iodine. But if you look at a greater distance, you see that iodine has more. The dose rate of iodine is more than that of palladium. Why? Because energy, the energy that I mentioned up here, these two energies have great effects in depth, you know. And let me also mention that low dose rate is between 0.2 to 4 gray. That's what is considered as low dose rate in the ICP-RU report. And with an energy of 27 kilo electron volts, by the time it's attenuated by the patient's tissue, there's no radiation left out. So it's an outpatient therapy. So the patient can be released after 3 days. In our clinic, we release a patient after the 3rd day after the implant. Professor Hesser already mentioned a lot of all these recommendations, and you also have the recommendation for from the ESTRO for the dosimetry of low dose rate prostate brachytherapy, which I'm not going to go into details. I'll just jump to the treatment planning of low dose rate brachytherapy, some of the nomenclature that we have in this modality. You have the pre-planning. The pre-planning is basically a plan created outside the operating room before the implant procedure. The intraoperative plan produced during single operating room procedure before implants. Then you have the interactive planning, which is a modification of the treatment plan based on the feedback from real-time tracking of the actual needle positions, because when the urologist is piercing the needles into the prostate, of course the prostate is moving. So with that movement, you also have to take that movement and deformation of the prostate. You have to take that into account. Then you have the dynamic dose calculation, which I would say we are not yet there. Actually, not so many clinics are doing that, which is just the continuous update of implant dosimetry with feedbacks from seat positions. Then you have the task group 64, which basically is the practical guideline for clinical and medical physicists. For our clinic, our PTV is equal to our CTV. We don't add margin to our CTV. Many clinics, they do add margin to their CTV. The dose parameters that we use the D90, which is the minimum dose received by 90% of the prostate volume. And this should be greater than 90% of the prescribed dose. V100, percentage of the target volume receiving 100% of the prescribed dose, which should be greater than 95%. The V150 should be between 45% and 65%. For the organs at risk, urethra, the D10 should be less than 150% of the prescribed dose, the D30 less than 130% of the prescribed dose. And for rectum, rectum in absolute, we do it in absolutes, which is recommended. This task group here, the tumor and target volume in permanent prostate brachytherapy from the Estro. All of this is well documented in this report. Here for the treatment, this is our criteria that we use in our clinic. We put this into the treatment planning system because when you are doing the plan, you want to be sure if what you are doing is, if the constraints of your plan are being met. I also try to also talk to also show the inverse planning that Professor Hesser also mentioned. I'll try to also demonstrate using this dosimetric quality alert. For there are different types of needle seat placement planning. You have the uniform loading, which is the Seattle planning approach, which is you just try to load seats into the prostata uniformly. Then you have the peripheral loading technique, which is good for the rectum for the urethra. Then you have the modified uniform technique, which is a mixture of uniform and peripheral planning, and the nomogram approach, which is what we use, which is loading 75% of radioactive source in the periphery and 25% in the inferior. Patient setup and factors. Of course, the patient is anesthetized. Patient is placed in the lithotomy position. Perineal area is disinfected. Stepper and ultrasound is set up. You want to make sure that people are not, because you might have colleagues that are walking around, and you want to make sure that the cables are out of the way, and that your notebook or your TPS is getting current all the time. Volume study, you want to make sure that there's no pubic arc interference. You have to take care of prostate movement. I'll also show that what we do with that is that we try to insert the first needles that we try to insert is at 9 o'clock and at 3 o'clock in order to hold the prostate into position. And when we are also loading the seats, we start with 9 o'clock and move to 3 o'clock, and then come back to 9 o'clock and continue downwards. Also have to understand that the prostate size also changes during the implant, so time is also a factor, because if you're wasting a lot of time, the bleeding can also affect the visualization of the procedure. And as already mentioned, edema is also a factor that can affect the implant dosimetry, which Frank Walter and others documented well, documented well in their paper. it's important that the team, that anyway, everyone who is involved in brachytherapy or in prostate, in low dose rate prostate brachytherapy, knows the patient selection criteria. It's very important. So with us, we do low and intermediate risk group. We don't do high group. The prostate volume should be less than or equal to 50 milliliter. This is an example of a patient that we treated some time ago, lying in the lithotomy position. It's also important, and the ordinance also states that once we are performing this procedure, the room is the control area. So you have to, here you see that on the door we place the radioactive sign so that each person, each individual passing by or who intends to enter the operating room is aware that the area is a control area, radioactive control area. So you have here, this here is the probe, the ultrasound on the on the stepper. Here you have the ultrasound connected to the TPS. Here is during volume study. You want to do volume study to make sure that the prostate is the size that was studied before the operation. I already showed this, so I don't need. And then dose reporting. Dose reporting is also very important. How do you report your dose? There are several recommendations. So you have to sit down with your team and then decide which recommendation do we want to follow. It's also important to verify the seed activity. With us or with the sources from bird, the sources, they have to be sterilized. So we are not able, we are, of course, we are able, but we don't want to play around with the source before the implant. So what we do is that we do the implant and then we verify the remaining seeds. So that's how we do it. Then we have this after the implant. Here you have the electrometer, you have the source check, you have the loader. That is the source check here. Then we have a sheet where we take down the patient's name, the activity, reference activity. Then we do 10 seeds, and then we compare it to the reference. And according to the recommendation, it should not be more than 3%. Radiation protection is also an important aspect that should not be neglected as well. When do you want to release your patient? When is it safe to release your patients? So using the 1 millisievert exposure limit to the general public, as stated in the radiation protection ordinance, one can calculate the dose rate at 2 meters. Actually, this should be microsievert per hour. It should be microsievert per hour, not absolute. So I mean, it's an easy calculation that can be done using the equation that was shown by Professor Hesser from the TG43. Yeah. As already mentioned, we release patient on the second day after the implant. All the individuals in the operating room at that time, they have skin bash because we want to also monitor them to make sure that none of them is getting any radiation. They are not being exposed to radiation. The patient, they carry along an information card. We treated a patient once from Moscow, from Russia, and we had the information card given to him in German. And at the airport, the alarm went on. So, and they had to cross-check him, and he had to present them with his card, so they couldn't really understand what was on the card. And fortunately for us, we had somebody at our department who could speak Russian, so had to talk with them, explain to them what the document meant. So it's important that your patients, they do carry along this information card as well, so that in case of anything, so that the people involved should know what activity they received, when they did receive that activity, and that there's no danger to the public. Survey meter. It's also important to know your survey meter. What is, what are the limitations that your survey meter has? We use the Berthold LB123 dose rate monitor meter. Here, if you look at this curve, you realize that here you have 0 and 45 degrees. You see that there is a directional dependency here. So you want to make sure that, okay, that you are holding the probe the right way in order to do your measurements. And also for this probe, it measures energies from 30 kilo electron volts. And for iodine 125, we have an average energy of 27 kilo electron volts. So this has to be taken into consideration as well. After our implants, we do documentation. Of course, we do electronic documentation, but you want to do an extra documentation for yourself as well, and for the department. So here we have where we put the patient name, we put the diagnosis, what the patient, the risk group of the patient, the PSA value, and so on, histology. Here we document we document the quality assurance that we made before the implant, before going into the operating room, and the quality assurance after the implant, and the intraoperative values or data, how many seats we used, how many needles, volume, the D90, all the things that I mentioned, the parameter that I mentioned here, the dose parameter. So we document all those as well. Then post-planning dosimetry. We do post-planning 4 weeks after implants. We do 2 millimeter slice thickness. We do CT and MRI. Why? Because with CT, you have this effect. You have overestimation. The red anatomy is the prostate from MRI, and the orange is that from CT. So if you are using that of CT, then you realize that, oh, suddenly my dosimetry was very bad. And then you start thinking of options if to do external beam therapy. So it's very important that that you know what you're doing, and if you don't have MRI, then you have to know, the doctor have to know how to go about contouring. And there's also recommendation from AAPM on post dosimetry parameter. D100, D90 should be documented. V200, V150, and V100 and V90 can also be documented. For the rectum and urethra, here you have the parameters that should be documented. Here, that's what we have in the treatment planning system, in our treatment planning system. Then, according to the regulatory authority or our regulatory authority, we have to document as well the remaining seats. How many remaining seats do we have in the department? How many have we sent back to the vendor? So what we usually do is that we send back the seats, the remaining seats, 3 times a year. So we document the treated patients, how many the total activities that they receive, the remaining activity, the serial number of the seats, and so on. So we do all this documentation. Here is a graphic, a plan of intraoperative. This is the intraoperative on your left, and the post-implant with the CT. So now I'll move to the. I hope I'll be able to do a demo with Variseed. Can you see my screen? Hello?
Yes, we can see the screen. We can see the screen. Demo and
okay. Yeah. Okay. So so this Variseed. For Variseed, when you get Variseed, as I mentioned, you want to do the various the commissioning is very important. You have to select your ultrasound, your video capturing device. You have to select that. You also have to select what kind of stepper you are using. For the templates, I mentioned the physical template, I mentioned the visual template, and that of the TPS. So you want to make sure that that you are importing the right template. Let's see, show it here, just to show you. So the vendor sends you different kinds of templates. So you see, if you are using the wrong template, if your physical template is from a different vendor of a different type, and you select something else, then you see that you'll be treating your plan, and what you are treating will be totally different. So that's that for setting up. Then you want to import the right source. Here, this is the source that we use. We use the BAT source STM1251. So you want to make sure that you have the right source imported with the right anisotropic factors, the right active length, physical diameter, physical length. So you want to make sure that all these things are right, and the right activity and conversion factors. Okay. You also want to make sure that the nomogram is also right. Nomogram is simply volume to activity. So you have, if you have a patient that has some, for example, 20 cubic centimeter, you be treating with an activity of 22.3 millicurie. So you want to make sure that all those things are right. So so I'll just give a quick demonstration of intraoperative planning. So here, let's say we have ordered our seed, we did pre-planning, we know the volume of the patient and so on, and we already placed the order and the seed is there, and we have a seed, we have seeds with activities of 0.45 millicurie. So you want to, of course, the feeds, you have the strength up here showing you 0.572. But you want to also, in that process, you want to be sure that what the treatment, what the TPS is doing at that moment, the conversion factor is 1.27. So you want to be sure that the TPS is converting correctly. So you just punch into your calculator 0.45 times the conversion factor to verify if the strength is actually 0.572. The prescription dose, structure, region, configuration, you want to make sure that it's right. I already mentioned the template, and what type of study are we doing? So here you have the intraoperative, and here you have post, here you have pre-op. So what we are doing is intraoperative. So say okay. So the system asks you, are you sure? This is a convention, you say okay. So now basically what I'm going to do here is just the theory that Professor Hesser already gave. So now we have to calibrate. This is just a simulator. So let's say we don't want to use this existing, let me just use the existing so as to save some time. I think I don't have so much time. So you see next. So you have to know the parameter of your probe, this distance, the longitudinal and the transverse offset. We use 0.5. So here you have to calibrate this. If it's calibrated, but we can change it if we want. Let's do that. For example, if you have something like that, then you'll be doing something totally different with your planning system. So you want to make sure that everything is calibrated accurately, that the grid is well aligned. Next, the scaling, okay, and everything is fine, and we say finish. Say yes. So now, this is our stepper. Here, with the stepper, we can, let me just go ahead and make this a little bit bigger. So with the stepper, we can do volume study. Now we can acquire our images. So what happened is that the radiation oncologist does our process, does the study. So okay, have this volume, and after doing that, click. You start acquiring your images. Where do you start acquiring your images? Usually what we do is that we start acquiring the image from the base. You have the base and you have the apex. So we start acquiring from the apex. So what we do is that we acquire two slides. That was just one slide. We acquire two slides so that someone who is going to control your plan can be able to tell if you missed out a slide of the prostate. So that's why we acquire a superior image with the bladder on it. So the doctor moves to the next, and you acquire, move to the next, you acquire, move to the next, do the acquire, move to the next. You are communicating with him. He moves to the next, and you tell him, yes, I have it. To the next, yes, I have it. To the next, yes. To the next. And we also do two slides. Because there was an incident, I think that was in the US, I don't know exactly where they were treating the pineal bulb instead of the prostate. So that's our way of verifying that we have the prostate and not something else. So we do two slides at the apex. So after doing that, you move to the next tab, which is the template registration. So you want to make sure that your template is well aligned to that of your ultrasound. This is the template of the TPS with that of the ultrasound. That is well aligned. Okay. And if that's so, you accept, and then you move on to contouring, where the physician then does the contouring, does the prostate. So you see the system automatically creates the contour of the prostate. So, and then next you go to your organs at risk. I'll just try to do this quickly. So here, let's say this is our ureter, and we do the rectum. What's very important is the rectum wall. That's what is very important here. Okay. So let's say this is our rectum. So now we are done with our contouring. So we move to source placement. So there are several ways that can be done. You can use the monogram method, or you can use the inverse planning. Okay, the inverse planning. Here you have the volume optimization, where you can. I don't have any. Where you can. No needle. Okay, I have to do needle first. So let's use the nomogram. So here you have the prostate parameter here. You have 3 centimeter length, perimeter, and the area. So let's say 3. And here you have this 75% periphery that I mentioned. Okay. So the interior needles, let's say we take 4. We don't want to be piercing the patient with a lot of needle. Let's take 10. And here you can scroll to see if you are doing well if what you selected is doing well or not. You can move this inner, the interior needles. And here you have additional settings, which I'm not going to go into. Here you have your activity. Okay. So let me just, you want to make sure that you're using the right dosimetric quality alert. Yeah. So here I have for intraoperative, and here I have for post implant. Okay, so I'm using the right one. Here you have, these are the isodose levels. So you have the isodose levels here. You see that we have a lot of red here. So we have to optimize so that we comply to our dosimetric alert. Okay. So what I usually do is I just take out the isodose that are not really important. I just, so as to have an overview of what I'm doing. And remember, this, you are in the operating room, and this has to go so fast. So you have to do the planning so fast because everybody is there waiting to start treating the patient. So they are waiting for your plan, so it has to be fast. Okay. So here you have the seat configuration inside the needle. This is my prostate. The black dark lines, they show me the extent of my prostate and where I have the needles and where I have the seeds. Okay, so at this plane, if I'm having my prostate, if I'm having this seed here, then at this plane, this seed is outside the prostate. So we want to make sure that we are in conform with our dosimetric alert. So normally what we do is we take out the seeds in the interior needles, but I'm not going to waste so much time doing that here. So I already have a plan that I already prepared. So let's say this, our patient already ready for treatment. You see that if I go through all my needles, see that the plan is well conformed. I have no red here. I have 99.10% for V100, which is really good. For D90, I have more than the prescribed dose, which is good. For the organs at risk, I'm also doing well here, which is fine. So move to the implants. So you want to make sure that your contour is aligned with that of the ultrasound. And then now you can tell, the medical physicist can tell the doctor where to start. The starting point is always important because if the communication is not done correctly, the urologist might think, oh, he said I should start with the second seat from the left, from above. Meanwhile, you are on the third seat. And suddenly you are on the third seat and you realize, oh no, he's here. So that's already a confusion. So at each step, you want to be sure that the whole team is on line with you. The whole team is on the same page. Okay. And after each implantation is marked as implanted, the implantation is done in the longitudinal view. Why? Because you want to be sure that that you are not placing the seed outside of the prostate or somewhere else. Here you have the 3D view of your prostate. You can change the color to see the plan that you did. You can also go to the dose volume histogram, which all of these you have to do in your quality assurance, because you are going to look at this to know if you are doing a quality implant, if you are treating the patient rightly. So that's why quality assurance is very, very important. Then to the continuous volume analysis, we are also not doing bad. Okay. So I think I should stop here. Any questions? Hope I didn't forget anything. So thank you for your attention.
Yeah, question time, please. Okay, does anyone have any question? Okay, I have a question here. It says you could add, okay, sorry. Iodine 125 or palladium 103. How does one choose the best seed type?
As I mentioned, there are many people who are working with palladium 103, and there are many that are also working with iodine 125. So it's something that you have to sit together with your team, and you have to assess what you have in your market, the accessibility, because there are many factors to it. What is the delivery time? And your patients as well. So for us, we have a vendor that can deliver us iodine, and the energy of iodine, we think from what I explained, the energy is good. The clinical relevance, the diagram that I showed here, what was that? Here. So these are all things that you have to look into. Did I answer the question well?
Yeah, thank you. So, any more questions, please? Okay. All right. From Adeniji, how do you handle missing or displaced seeds?
That's a good question. Missing or displaced seed. I mean, we have I think 3 incidents where the seed was not placed rightly. So what we do is that's why intraoperative planning is a good thing, because when it happens, then you can make adjustment to give a quality treatment. So what we do is, with misplaced seed, is that we try to place the seed where there was an underdose, where there is an underdose. So that's a good thing with rate time planning. We haven't had incidents with missing seeds. So what we usually do is that there's always a communication between the person configuring the seeds and the medical physicist. So each time we are implanting the seeds, I'm always getting feedback. How many seeds have we implanted? How many seeds have you configured? So in that way, we are able to cross-check, and immediately we realize that we are not on the same page. So we go back to find out where the mistake was. There was a case that with the loader. Somehow the loader, the needle in the loader was a little bit bent, so we couldn't configure the seat rightly, so the seat went missing inside the loader. So we had to dismantle the loader immediately, and we could recover that seat. So it goes back to communication. You always have to communicate with your team.
Thank you very much. Okay, any more questions, please? Okay. Please, can we adopt the patient information card so we have it translated in English?
Yeah, of course. I mean, yeah.
Okay. All right. Thank you very much, everyone. Any more questions, please? Okay. In the absence of any more questions, please, I want to say I'll make this video available as soon as we can. So we are going to make it available also in a YouTube channel. We are having a YouTube channel right now. So we can always view the video anytime we want to. All right. Thank you very much, Dr. Hesser and Dr. Ernest Okonkwo, Mr. Ernest Okonkwo. Okay.
Thank you too.
Thank you. Bye.
Yeah, bye.
Yeah.